This is Saxon, Advanced Math, Lesson 76.c, and we're going to be working with Trigonometric Identities. It also has 76.d, which is Rules of the Game, and we're going to start out first with what an identity is. In algebra, if we had a conditional statement like this, x plus 4 equals 7, this is true only if x has one unique value. What's the value for x? 3, right? And this only works for 3. This is not an identity, it's just an algebraic expression. It's just conditional. It only works if x is 3. Now we solve it, and we've done this all through the year, right? And this is something we've done quite often. However, sometimes when we get to another type of problem, which is like we have a linear equation laying on top of another linear equation, they're exactly the same equation, and we have called those an identity. Why? Because every single value you put in for x is true. For instance, 2x minus 3 equals 3x minus x minus 3. Any value is true for this. If I reduce these down, I end up with x equals x, or 3 equals 3, or whatever. But let's go ahead and plug in a value. If I put 3 in, I said 2 times 3 minus 3 equals 3 times 3 minus 3 minus 3. Guess what? 3 equals 3. If I do the same thing with 1, 2 times 1 minus 3 equals 3 times 1 minus 3. I get negative 1 equals negative 1. It's an identity. It always works for every single value. Now, there are a couple exceptions to that. Division by 0, when you have a equation that you would have a denominator or a denominator equal to x, or a value that would cause division by x, that is an excluded value to the identity, and that's when we would not use that as the terminology. Now, in trig identities, when we get into these, that's exactly how we think of it. Two forms of an expression that have identical values are called trigonometric identities. That's if they have trig in them, of course. And we're going to stay away from using 0 as a possibility. Now, 76.d says rules of the game. And these are what we're going to be doing for solving an identity or proving something to be true or showing that it's true would be a better way to put that. So if I look at it, first of all, I'm substituting an equivalent expression for any part of the given expression. Multiply the top and the bottom by the same non-zero quantity, right? I can't do that by a 0. Okay? If I multiply it by a 0 quantity, I negate this and it doesn't work. Just like if I did it up here. It wouldn't work on this one. I get up with 0 equals 0, or the x's all cancel. But if I had that in the denominator, it would not. And then 3 combined terms that have equal denominators. So let's look at the example 76.1. They asked us to show the cotangent of x over the cosecant of x is equal to the cosine of x. A couple of things, ignore my arrows and drawings. I know it's confusing at first. We have to put some bases down. First of all, we know the cotangent is equal to 1 over the tangent. The secant is 1 over the cosine, and the cosecant is 1 over the sine. I also have to remember this little piece, and unfortunately I don't know why the book didn't remind you of that. If you're watching and following your book as you should, you'll have to write this in the margin if you want to, and that's the tangent of theta equals the sine of theta over the cosine of theta. We will use that a lot with trig identities. Unfortunately, they failed to mention that in this lesson. I think they do a wonderful job, but they expected you to already have that memorized, and then this problem would be very difficult to follow in the book if you didn't know this. So example 76.1 says show the cotangent of x over the cosecant of x is equal to the cosine of x. Now, I'm going to use my tools, right? Here's my first couple tools. 1 over the tangent is equal to the cotangent, and 1 over the sine is equal to the cosecant. So I plug that in. Now I move the cosine of x to the left-hand side, get it out of my way, and I made this into putting the cotangent of x over the cosecant of x right here in the middle. The next thing I do is I start substituting. That's what my arrows are for. Notice that I'm just saying, oh, I know what cotangent is, 1 over the tangent. I know what cosecant is, 1 over the sine, and I plug those in. Okay? At this point, this is where you've got to be paying close attention. You realize, oh, do I know what the tangent is? Sure, tangent of theta or x is the sine over the cosine. So I plug that one in. So I've gone from here, I plugged in my numerator and my denominator, and then I realized, oh, my tangent is the sine over the cosine. Once I have that, I have 1 over the sine over the cosine over 1 over the sine. Well, that looks confusing. If it was just the numerator there, I think you guys would realize that 1 over something is the same as if I inverted and multiplied the top and the bottom by it, or some people remember as they can jump 2 levels. But this equals this, cosine of x over the sine of x. over 1 over the sine of x. Well, how do I get this out of here? Once again, I either jump 2 levels or I realize I multiply by the inverse. So, inverse over the inverse is that's why we're doing step 2 here. I'm all the way top and bottom, the same non-zero quantity. What is a non-zero quantity? Sine of x over 1, sine of x over 1. Well, what value is that? 1. And so it's a non-zero quantity. When I do so, I'm left with the sines cancel. Sines cancel. I'm left with cosine of x over 1, which is cosine of x. Guess what? That's what I was trying to prove. So this is the steps for proving or showing that the cotangent of x over the cosecant of x equals the cosine of x, using just these as my tools. And keep in mind, we'll build this tool set. We'll start memorizing some extra identities to put in here, but this is just showing how to do that. And yeah, it works out the same every way. Couldn't you just memorize all these? Sure, it's just a lot to memorize. It's a little easier to memorize our couple of basic identity terms. And once again, this is an identity, right? Because these are equal with different terminology, but they are the same. It's an identity. It's not a conditional statement. No matter what I put in for theta, it works on both sides. It's a trig identity. So the 1, 2, 3 trig identities here. This is a trig identity here. So I have the 4 trig identities that I started with, and I'm able to go ahead and use those 4 identities to show this to be true.